I have one. I sent a message to everybody, so I'll just show you that. I sent this message to everyone, so it's about extra help. So we will have help sessions for students Monday, Tuesday, and Wednesday evening, 7th period. 7th period begins at 7:45. The rule is that if no students show up by 8, the TAs can go home. So please get there before that if you want to ask questions about homework or class. If you cannot make it during any of these times, you can contact me and I'll meet you separately. I also recommend Khan Academy for general math issues. Also, please make sure you have registered for our class through Blackboard, because I often post stuff there and send announcements from there. The name of the class in Blackboard is here. And finally, as a reminder, if you want to send me email, generally it is better to send mail to the TA first. If they cannot help you, then you can contact me. Okay? So, and also we have a new assignment, which is due assignment here, called Annuities, which is due on the 19th. Okay? Any questions? Okay, and today we're going to talk about that assignment, and also we will talk about compound interest. So let's start with compound interest. We did this a little bit, but I just want to make sure that we cover it clearly. So we have simple interest, and that's what we covered first, and then we have compound interest. What's the difference between these two? What's the difference between simple and compound interest? Anybody say? Ready? What's the difference between simple and compound interest? Just any kind of description you want to give. It doesn't have to be, well, it doesn't have to be a formula. In fact, I don't really want a formula. I just want to know what you think is the difference. Anybody? I thought we covered this. I know we covered it in the video that I delivered, sent you all.
Simple.
What?
Simple is simple interest. Like if you got interest,
Yeah.
so like I did like annually or year.
Okay.
So like if compound, you got interest 1 month, and then like the next month that interest will put more interest.
Right, that's exactly right. So simple is where you're not talking about leaving the interest in the bank. So you take it out, you keep it in your pocket, but you don't get interest on your interest. Whereas if it's compound, you're talking about leaving the money in the bank. So as you leave the interest in the bank, it becomes the new principal, the new amount in the bank, so you get interest on the original amount plus interest on the interest. And that accumulates more and more, and that's called compound interest. Okay? That's the basic idea, right? Now, what was the formula for simple interest? The future value, we want to write it in terms of future value, present value, RT. So, first of all, what do these symbols stand for again? FV stands for future value, PV stands for present value, R stands for interest rate, but you should say it more clearly than that. Interest rate, what? Per year. We have to be clear because other people will think it's not per year, but it's per year. Okay? And T is time, but you have to be more clear. Time in years. So the formulas that we derive are based on these being these particular things. That T is time in years, that R is interest per year. So, I mean, we could have said, okay, R is interest per period or whatever, and we would have just gotten a different kind of formula. But, for the formulas that we have, we need to know what each thing is. Okay? So, we do. By the way, I think in some of the videos in the textbook, he uses P for present value. I think I saw that when he was doing some of the videos. So, he might use P instead of PV. But in the text itself, they do use PV. Okay, so then, what in simple interest we're talking about, you have a certain amount of money that you put in the bank, and you have a certain interest rate that you're allowed to get, and you put it in for a certain amount of time. And you're hoping to know what? The future value of that, right? And the formula was what? Or that future value is what? What? Present value? What? Okay, that was one way, but even the more basic way, but I'll get to that one afterwards. But one other way to say it was this, right? It was just the present value plus the interest. That's the simplest way to understand it, right? Just the present value plus the interest. But what was the interest? Was what? PVRT, right? Right? So then the future value becomes PV, and I'll just jump to the last form now. PV 1 plus RT. Okay, so I skipped one step, but we did it before, so I don't have to do it again. So, okay? So this is for simple interest. Okay, so now let's talk about compound interest. So for compound interest, we start out just asking what happens in the first year. So in the first year, there's nothing to be compounded, right? You're just going to get your interest at the end of the year. That's the scenario I'm talking about. It's not dividing the year into 3 parts or 4 parts or 12 parts. You're just going to get your interest at the end of the year. So what do you have? The future value at the end of the first year is what? Maybe I'll make this notation. Future value 1. That means the future value at the end of the first year. So what is that? Well, it's the same thing as that. Right? It's PV. I guess maybe I should do this. I think I'll do this. No, that means at the end, so I'll just say PV. Yeah, I think I'll do that. PV0. How about PV0? PV0 is going to mean what? Present value at the beginning. Okay, let me make that. Okay, and then times 1 plus RT. Right? Everyone agree? Okay, now we want to continue to do the next year's calculation. So what do we say now, though? What do we say now? Again, it's sort of the same calculation again as the simple interest one, except for one small difference. And that is that PV is not the original PV, but it's the future value after the first year, right? That's the new PV. That's how much you have in the bank, right? At the beginning of the second year, how much money do you have in the bank? Do you just have PV? No, I mean, do you just have PV sub zero? No, you have more than that now, right? You have this amount, right? So we have to say that's how much we have in the bank, right? So if I want to calculate the future value at the end of the second year, how much did we have at the beginning of the second year? We had FV1, right? And then we just have the same formula, 1 plus RT, right? Everyone agree? Now T, I'm not sure I'm doing the T right, but I think it's okay. But what is FV1? Well, it's right here. So it's PV0, 1 plus RT. So that's this, right? Right? And then I have to do this. And then I can simplify this as what? PV0 times 1 plus RT squared, right? Okay, so that's FV2, right? Okay, now what do I want to calculate? The end of the third year, right? So what's that? How do I denote that? FV3. And what's that? Well, that's how much I have in the bank at the beginning of the third year, and then I get some interest on it, right? So how much do I have at the beginning of the third year? FV2, right? I have FV2, and then I get the same thing, 1 plus RT. Hope I'm doing this right. The T. Okay, and so, but what is FV2? It's here. So it's PV0, 1 plus RT squared times, so that's, this part is here, right? And then times 1 plus RT. Which gives me what? Okay? So you can see the pattern, obviously. So at the end of the third year, it looks like that. So at the end of the fourth year, it's going to look like what? It's going to have an exponent of 4. And at the end of the fifth year, it's going to have an exponent of 5, and so on, right? So at the end of n years, so I guess I'd say the future value at the end of n years is what? PV0. Now, maybe I'll take away the 0, just to say PV. It's just the beginning. PV times 1 plus RT to the n. Okay, and that's the compound interest formula, and that's not the same as that one, right? It's different. It's 1 plus RT to the n. Okay? So that's different. All right, any question about that? Any question? Anybody confused? Okay. Now, want to make one more, or improve it a little bit more, and that is, we want to allow for the bank to offer us interest a number of times every year, like twice a year, or 4 times a year, or 12 times a year. So we want to allow for the bank to do that. And then we want to get the formula for that as well. Okay? But it's going to be the same logic as we have here. Okay, let's see it. So this was compounding one time per year. Okay, but we want to allow a little bit more flexibility and allow for compounding more than one time a year. So by the way, what is what does the word semi-annually mean? Semi-annually means 2 times a year. What does the word annually mean? 1 time a year. What does the word quarterly mean? 4 times a year. By the way, how long is a quarter? 4 months? No, not 4 months, right? 3 months, right? A quarter of 12 is 3, right? So 3 months is a quarter. So the first quarter goes from when to when? I guess it goes from January to March, right? January through March. Okay. Anyway, and how about monthly? Of course, how many times is that? Obviously 12, and so on, right? Okay, so now we want to add that little bit of extra flexibility. Go ahead and talk about compounding. Let's say m times per year. We still want to calculate the future value. This is all about the future value. Okay, so what are we going to do now? So we're going to do the same logic, but we're only going to do it 1 period at a time instead of 1 year at a time. So it's really the same thing, right? We're just going to focus on 1 period at a time instead of 1 year at a time. But otherwise, do exactly the same thing we just did. So, what is the future value? All right, let me write it this way. 1p. What do I mean by 1p? First period. At the end of the first period, okay? Can I make up that notation? Or should I make up another notation? Maybe p is confusing because we use it for present value. What could I use instead of 1p? Give me another thing, if you don't like p. What? No, but I want a letter along with it, to say that it's the first period, and the second period. Okay, how about, I'll call it 1 per. 1 per. So that means first period. Okay, can you agree with do you accept my notation? Okay? Alright, so what is the future value at the end of the first period? So it's basically, it's just the simple interest formula. Right? So, in other words, what? It's the present value, and I'm not going to do this anymore. Whatever, I'm just going to use PV for the present value, times what? What's the formula for simple interest? 1 plus RT. Okay, but there's something wrong here. By the way, do I have the right formula here? Let me just make sure. I forgot to check this, so let me do it. This. Just want to make sure that I have the right formula here. All right, while I'm waiting for that, yeah, I have the right formula, I think. Okay, so anyway, what happens here? I think I don't need the T in there. Yeah, I think I don't need the T. Because T is only one, always one. So I don't need the T here, by the way. Okay, because T is always one. Is that right? Yeah. It's that. Sorry about that. Okay, I don't need the T there. And also, I don't need the T here either. It's 1 plus R. It's just 1 here. Or, wait. This is wrong. Yeah, that's right. Okay. Now, so, but what's wrong with this? Even with it, after I got rid of the T, what's still wrong with this? What? The period? No. What's wrong with this? Huh?
R.
R. What's wrong with R? Yeah, R is the interest rate per year. So let's suppose R was, suppose we got really lucky and we got 12% per year, right? Suppose really super great bank, and they gave us R is equal to 12%. Okay? Now, suppose that I'm talking about compounding it semi-annually. Okay? So should I, is this the right thing? For the first period? At the end of the first period? Is that how much I'm going to get? No. What am I going to get? What? How much? Just 1%, right? Why is it just 1%? Oh, I'm sorry, I said semi-annually, not 1%. 6%, right? Why is it 6%? Because it's 12, but they don't give us 12 two times. That would be like giving us 24%, right? They give us what? 6% after the first, after the half year. So it's not, this is wrong, right? So R is wrong, so how do I fix it? R divided by 2, right? Right? But how about if I want to be more general, so I don't want to just say work with semi-annually, suppose I want to say quarterly, then what would it be? R divided by 4, and suppose I want to say monthly, then it would be R divided by 12, right? So if I say M times per year, so M could be 4, M could be 2, it could be 4, it could be 12. So how do I include that? M. Where do I put the M? Here, right? Right? M times per year. So if M is twice, then it's 12 divided by 2. If it's 4 times, it's 12 divided by 4. If it's 12 times, it's 12 divided by 12, right? Okay, so that's the formula, right? At the end of the first period. Or the first, right? Okay, so then we have that much money, right? Then what? Then I want to calculate what it is at the end of the second period. So what's that? Well, it's what? So how much do I have at the beginning of the second period? I have this, right? So that's my new present value, right? So that's PV times 1 plus r over m. That's my new present value, right? And then I need to multiply that by what? 1 plus r over m, right? That's how much I'm going to get at the end of the second. So that's squared, right? Okay, so that's at the end of the second period, right? And then what? Now I want to do the third period. So what's that going to be? FV third period equals, this is the new present value at the beginning of the third period, so it's PV 1 plus R over M squared is the new present value, that's how much I have in the bank. And then I'm going to get interest on that, so I have to multiply that times 1 plus R over M, so what do I get now? Cubed. Okay? And I keep doing this, right? And I do this for t years. That's what I want to know. What's the future value after t years? That's the question. So if I want to know that, the answer to that, how many times am I going to do this? So let's just make it concrete for a minute. Suppose it was 5 years and m was equal to 5 years and m was equal to 12. In other words, I'm doing it monthly. I'm doing it 12 times per year. So how many times am I going to do this then? How many periods am I going to go through? 12 in the first year, but how many in 5 years? 5 times 12, right? So what's the coefficient going to be? 5 times 12, right? What the coefficient is going to be, what is 5 times 12? 60, right? 5 times 12. 60, right? So, So I'll change from 3 periods to 5 years. Okay, I could say, instead of 5 years, I could say 60 periods, but I just want to say 5 years. Okay, is what? PV 1 plus R over M to the 60. Does everyone agree with that? Is that right or wrong? Okay. And then to be just a little bit more general, FV for t years, can you read this or is this behind the screen? Okay, FV for t years, we just did it for 5 years. What did we get? R over M and 60. Where does the 60 come from? 12 times 5. But what was the 12? What was the symbol for 12? M. And what was the symbol for? What is the symbol for 5? T. So it's not 5 times 12. I'm sorry, it's not 12 times 5. It's what? M times T. So it's this, right? It's going to be M times T there. It's going to be 1 plus R over M and B. Okay? So what's that? That's the formula for compound interest, where you can compound more than once per year, like M times per year, and T stands for the number of years. R stands for, again, what? What does R stand for? The rate per year, right? It's important, right? Because we have this rate per month, per period, it's different, right? So it's the rate per year, T is the number of years, M is the number of periods, and that's it. Okay, now sometimes they use little I to stand for the rate per period, the interest rate per period. So, for example, if it was 12% and it was semi-annually, how many periods is that? 2 periods. So what's the interest rate per period again? 6, right? But if it was 12% and monthly, what would the interest rate per period be? 1%, right? So what's the calculation for I? R over M, right? Okay? 12 over 12, 12 over 2, whatever. Okay? And sometimes they use N to stand for the number of periods. So what was the number of periods in this calculation? 60, right? 60. Right? What is the general formula for the number of periods? It's the number of periods, the number of periods per year times the number of years, right? What's the symbol for number of periods? M. And what's the symbol for number of years? T. So this is MT. Right? So how can we rewrite this now? FV equals PV times 1 plus what? 1 plus R over M is written as I, and MT is written as N. So that's just another way of writing it, right? Okay? So that's the compound interest formula. Any questions about that? Now suppose they said to you, okay, so that tells you, like, if you put the money in the bank, how much you're going to have in the future, right? So suppose you wanted to know, how much money do I have to put in the bank now to have $1 million in the future? Well, that's not a good enough question, because in the future, how long in the future? I have to say how long. And I have to tell you the interest rate. And I have to tell you how many times a year they're going to compound it. Okay? So, if I ask that though, suppose I say with these crazy numbers, like 12%, which is a totally crazy number. But suppose you got 12% interest, and you got it, and so let's suppose they compounded it monthly. Why not? So how much money would you have to put in the bank to have $1 million in 10 years? Right? You understand the question? So then, which of these is not known? Is this 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 not known? Which one is not known? I'm saying, how much money do I have to put in the bank now? So that's what I don't know, is what's in there now. That's called PV. So PV is not known, but hopefully all the other parts are known. What are the other parts? What's FV then? $1 million. I said, how much do you have to have $1 million? And what's R? 12%. I said, suppose it's 12%. And what's M? 12. I said, compounded monthly. And what's T? 10 years. Okay, so everything is known except for PV, so you should be able to find out what PV is. Right? So you could do that calculation without much trouble. Okay, any questions about that? Okay, now here is the formula. Can you see this? No. Thank you for your honesty. No, sorry, just kidding. Not honesty, for your candidness, is what I meant to say. Okay, now can you see it? What does it say? It says what we just did, right? That's the compound interest formula, right? Same as I wrote on the board. In fact, it's the same, no, not the same problem. Anyway. Okay, now, look at this formula. All right, let's look at this. What does it say? Let's read it. Find the future value after 5 years. So what's T equal to? 5. Of a $10,000 investment. So what's that tell me? This is called what? PV investment earning 6% interest, that's R, with interest reinvested every month. That's what? Every month means M, right? M equals 12, right? Everyone translate that, right? So PV is equal to that, R is that, M is that, T is that. We get this formula here, we get this. Okay, the answer is 13. 488.50. Okay. All right, now, they say, let's write this as a function of time. What does that mean, a function of time? How about, the number of APU students? Is that a function of time? No? The number of APU students is not a function of time? What does it mean to be a function of time? That's just another way of saying that it depends on time, or that it changes over time. So does the number of students at APU change over time? Yeah, right? Students drop out, then they have new enrollment at the next year, so it's changing over time, right? So the number of students is a function of time, right? How about the future value? Is the future value here a function of time? Yeah, of course, right? In fact, here it is, right here. It's a function of t. Can you see that? What does it mean to say that it's a function of t? It just means that it changes over time, which of course it does. That's how everything we've been doing is just based on that idea that the money that you have is changing over time. Right? So of course it's a function of t, right? And we leave the t here. So they still have 12. 12 means what? Why is the 12 there? That's the m, which is what? The number of compounding periods, right? So we still leave, they just leave that there. They're going to still compound per month, or every month, but they're leaving t out, so they could do it for t equals 1 year, or 2 years, or 10 years, or 100 years. Okay? And obviously it's going to change over time. The future value is going to change. In fact, is it going to increase or decrease, the future value? Of course it's going to increase, otherwise people wouldn't leave their money in the bank, right? So, it's going to increase. But it's a function of time, right? Okay, now, of course we can just add this 1 plus this, right? And collapse that to a simple number. So that's what they did here, right? Which is 1.005. So we get this a little slightly more simplified looking thing, right? Alright? And this is a function of time. Now normally we don't use t as our variable in math. We usually use what letter? X, right? So let's imagine this wasn't t, let's imagine it's x. So this is an x up here. So I'll ask you, where is the variable? Where is the x? Shh, please stop playing with your phones and talk. Where is the x? Or where is the t? Is it in the, isn't it in the exponent? Right? Now, didn't we talk about exponential functions before? And didn't I tell you that exponential functions grow really, really fast? And this is actually an exponential function because, forget about the 10,000. You have some letter here, some number here, and then t is in the exponent. Right? Forget about the 10,000, you can ignore that. That's a minor part of this. So just simplify it by getting rid of that. So this is an exponential function. So what does that mean? It means it grows really a lot. Okay? And that's why, remember we said that if you put $1 in the bank at the time of Jesus Christ, in other words, 2,000 years ago, and you got like a simple interest rate, I mean a mild interest rate, and let's suppose they compounded it 12 times per year. I said, how much would it be worth? Remember what I said?
3 earths of gold.
How much?
3 earths of gold.
And I think I said 100 or 1,000 earths filled with gold. That's what I've heard. I've never done the calculation myself, and I forget whether it was 100 or 1,000. What's the difference, 100 or 1,000? 100 or 1,000 golden earths. Anyway, the point is it's a lot of money, right? And why is it so much money? Because the exponential, because that we're talking about compounding, compound interest, and compound interest shows the exponent where? In the, shows the variable in the exponent, and so it's going to grow super fast. That's why it becomes so much money. Okay? And this is a picture of the graph of this function. So before I show you the picture of the graph of this function, tell me what is the x-axis going to be labeled as, and what is the y-axis going to be labeled as. I'm going to show you a graph of this function. So FV equals da-da-da-da-da. Now, so before I show it to you, just what is the x-axis going to be? In other words, what's the horizontal axis going to be? And what's the vertical axis going to be? Normally it's what? The horizontal axis is x, and the vertical axis is y. But we're not doing x and y here, so what is the horizontal axis going to be? T, right? And what's the vertical axis going to be? FB. Okay, so what's this graph look like in the TFB plane? Right, normally we say the XY plane, but it's not the XY plane here. It's the TFB plane, so what's it going to look like? Looks like that. So that's kind of that is an exponential function. Okay? So, looks like that. Okay? Any question about this? So this is a graph of the way your money would grow over 10 years, 20 years, and so on, under these conditions. What were the conditions, by the way? There's $10,000, 6% interest compounded monthly. Okay? Any questions about that? That's what it would look like. Okay, let's go on to another problem. So this is the one we also just did, where we wanted to know, we knew the future value, and we wanted to calculate the present value, right? Like, I want to have $1 million in the future, what's the present value I need now, right? That kind of thing. So that's just that one. Okay. Okay, now here, this is called a question about zero coupon bonds. Okay, which we talked about bonds before, and I think some bonds give interest and some bonds don't give interest. Okay? But what was the main idea of a bond? So you buy a $1,000 bond from U.S. Treasury bond, well, I think they call it T-bills. You buy a $1,000 one, and it matures in 5 years. So remember I said, are you going to pay $1,000 now for that? No, that would be a good idea. But you might pay $500 for it. Then you'd be pretty happy, I think. Right? $1,000 bond in 5 years, $500 now would be a great deal. Right? So what's the idea? That you'd earn a lot of money or the value of the bond would increase a lot from what you paid to what it's finally worth. Right? And the terms for that are the maturity value, or the face value, or the par value. I think they all mean the same thing. So that's the $1,000 is that. So the face value or the maturity value or the par value is $1,000. And then you pay some certain amount of money for that. That is called, anybody know what that's called? I forget already. What is that called? I forget. Anyway, but there's a certain kind of bond called a zero coupon bond. And that, it turns out what that means is it doesn't pay any interest like every month or every 6 months or anything like that. It doesn't pay interest. In other words, there are some bonds that do pay interest in addition to the fact that you can buy them at a cheaper price and redeem them at a higher price. They also pay some interest every month or every year, whatever it is. And that used to be, I think, they used to have little coupons on them that you could tear off, and then you go to whoever issued the bond, like the U.S. government or somebody else, and you say, okay, here's my coupon, they have to give you the interest. So it's called a coupon bond. And a zero coupon bond is one that doesn't have that. Okay? So the only good thing about the zero coupon bond is not the interest, but the value that it gets to at maturity. Okay, any questions about that? So, let's look at this example of a zero coupon bond. Megabucks Corporation issues a 10-year zero coupon bond. Okay? So, what's another, can anybody tell me the name of it? Do you know any corporations? Okay, so countries often issue bonds. Does anybody know any corporations that issue bonds? Anybody know? Well, big corporations sometimes do. They're like Toyota. You can get Toyota bonds. Okay? And again, why do they do that? Because they're borrowing money from you. Okay? So they just want to get some money in advance. Okay, so Megabucks Corporation is doing the same thing, is issuing a 10-year zero coupon bond. How much would you pay for bonds with a maturity value of $10,000? What does that again mean? What does the maturity value mean again? That's the face value. That's what's written on the bond. That's how much you can redeem it for at the end of the period, at the end of the time. Not now, but at the end of in this case, at the end of 10 years, you can go to Megabucks and say, here's my bond, give me $10,000, and now they have to give it to you legally. Okay? So, but the question is, how much should you pay for this bond now, 10 years before, if you wish to get a return of 6.5% compounded annually? So what are they asking about here? They want to say, if you get how much do you have to pay now so that if, in effect, you're getting 6.5% compounded annually? So like, suppose I paid $5,000 now, right? If maybe 6.5% would mean that after the first year, it was worth $5,300. And after the second year, it was worth $5,800. And after that, right? So 6.5% is going to imply a certain growth, right? And what we're saying is, how much should we pay so that if we start at that amount and we do 6.5% interest, that eventually it would be worth $10,000. Okay? You understand? Or another way, why are they asking that? That's kind of a weird question. But another way to think about it is, suppose that you could get 6.5% compounded annually in the bank. So if you know what the equivalent, how much you should pay for this bond to get that, suppose the bond was selling for less than that. Then you say, oh, I should buy the bond instead of putting it in the bank. Is that clear or not? Did I say that clearly or not? Let me say it again. Suppose that you could get at the bank, the bank was offering you you go down to Oita Bank and they say, okay, I'm going to give you 6.5% interest, and we'll give it to you compounded annually. Okay? So you say, okay, that's good. Okay, I'll keep that in mind. Maybe I'll do it, maybe I won't. Now the question is, there's a bond out there that you can buy, and suppose that it's a $10,000 bond that matures in 10 years, and it's currently selling for $6,000, or let's say it's currently selling for $7,000. Okay? Should you put your money in the $7,000 bond that becomes $10,000, or should you put your money in the bank? So I don't know the answer to that. But you might get a question like that, right? You might have a situation there. So what are they asking you to figure out? How much you would pay for the bond in order to get the same, basically the same rate that you're getting at the bank, right? So suppose it turns out that you should pay $5,000 for the bond to get the same rate that you got at the bank. But suppose the bond was actually selling for $4,000. Then what? I would say, oh, instead of putting the money in the bank, maybe I should put it in the bond. Except then you have to think about, is the person that's issuing the bond stable or not? Right? If it's like Toyota, it's probably pretty stable. They're not going to go bankrupt, right? So you have to consider that, but we won't think about that. Okay? So how do we figure out the answer though? How much should we pay? Well, we're just going to use the same formula that we've developed. This one. Here. Our compound interest formula. The only question is, what are the things that are known, and what are the things that are not known? What are the things that are known, and what are the things that are not known?
Present value.
The present value is unknown, right? Hopefully all the other stuff is known. Right? So we should be able to figure it out. In fact, that's what they do here. Right? Okay? So that's that one. Okay, now here's something a little bit complicated, but you guys are APM students, right? So you're business majors, right? I was never a business major. I never took one business course. I avoided every business course. I would never have taken even one. Yeah. So, but you guys are not me, I think. So, anyway, so the thing is that, so you're business students, so you need to know these kinds of terminology sometime in your future. You may as well read it here. I'm sure they'll cover this again in your finance class, but let's see what they say. So this is kind of confusing. Particularly in financial applications, you will hear the word discounted in place of compounded. That sounds so confusing to me. I don't know where they came up with this, saying that. Discounted in place of compounded. When discussing present value. So I guess since they're talking about discussing present value, so the thing is, when we talk about future value, we're talking about compounding, right? But when we know the future value, and we want to figure out what present value we would need, or something like that, maybe discounted might make some sense, I guess. So let's see what they mean again. Thus, the result of example 2, which was this example here, zero coupon bond, $10,000, 6.5%, 10 years, all that stuff, all of this. The result of this, which was this, by the way. Let's read the number. What was the number? How much would you pay now to get $10,000 then, 10 years later? 5327.26. $5,300 and something, right? Right? But that was based on a very high interest rate, and so you wouldn't normally get such a good interest rate, so I think be different. Okay. Anyway, thus the result of example 2, that is this 5327.26, might be phrased. Okay, let's read this. See if we can make sense out of this. The present value of $10,000 to be received 10 years from now, well, that's already what we said, with an interest rate of 6.5% discounted annually. Okay, I guess I can make some sense out of that. Discounted annually. So it's like, because we're going backwards, so we say kind of discounted annually instead of compounded annually. So compounded annually kind of implies, starting from the lower part and going up higher and higher. And here, since we were asked how much we know what we're starting with and we want to go back, they're using discounted. Okay? It's kind of awful, but okay. That's what they do, so you have to do it too. Okay, so the present value, so all the way up to here, it's the same language we would expect. The present value of $10,000 to be received 10 years from now. The present value of $10,000 to be received 10 years from now, with an interest rate of 6.5%, then it is discounted annually, is that 5327.26. Okay? Alright, so you've learned that too. Okay, inflation. What does inflation have to do with what we've been talking about? Well, we've been talking about money increasing based on how much is in there, right? And that's exactly what inflation does too, right? If you say 5% inflation, what do you mean? So from the amount that it's worth now, like you might say prices are moving at 5% inflation. So the price it is now, what happens? It increases by 5% after 1 year, and then what? At the end of the second year, it's 5% of what it was at the end of the first year, right? So it's exactly the same thing that we were talking about with compound interest. So exactly the same formula will apply to inflation, right? I don't think they usually talk about inflation compounded monthly or something, they never do that. But anyway, it's the same idea, okay? Oops. Any questions so far? Okay, let's go to this one. Constant dollars. Another one. Another business word that we don't have to cover here, but you have to learn it anyway. So I'm kind of interested in it, so let's do it. Okay? So constant dollars. Inflation in North Avalon is 6% per year. Which is really more expensive? A car costing $20,000 today, or one costing $22,000 in 3 years? So why would we say that a car costing $20,000 today is more expensive, please, than a car costing $22,000 in 3 years? Why would we say that? That doesn't make sense. 20,000 is not more than 22. What's the additional factor that I'm not thinking about? The inflation, right? There's some inflation. We're talking about that there's inflation. So, how do we know which one is more expensive? How can we do that? Anybody strategy for doing that? Anybody have a strategy? For deciding which one is more expensive? The 20,000 today or the 22,000 in 3 years? Huh? How do we, I want to know how you get the answer. How do we think about it? What? Find the future value.
Future value of 2000.
Okay, yeah, exactly. So he said, find the future value of 20,000 based on what? 6% increase per year, right? And that will work, right? Except they don't do it that way, do they? They do it, oh, they do it the other way. So they're going to work backwards on the 22. Okay? So they're going to say, suppose that 22 is the future value, what would the corresponding present value be? But it's the same thing as what you said, right? You could do it either way, right? So they do this. By the way, what's that minus n doing there? I'm confused. What's the minus n? We didn't have any minus n. We didn't have any minus n. What's the minus n doing there? Because if I want to solve this for PV, what do I do? Divide by this part, right? So bring it over to the denominator here, right? And then if I want to bring it up to here, just make it minus n, right? So, okay, so what are they doing here? They're saying, suppose the future value of something is 22, what's the present value? What's the answer? 18. So which is, what was the question? Which is more expensive? The 20,000 one today is more than the 22,000 one in 3 years, given one important fact, and that is inflation is 6% per year. Okay? All right, any questions about that? Okay, let's go on. Oh, let's read this. Before we go on, in the presence of inflation, the only way to compare prices at different times is, and this is just what we just did, to convert all prices to constant dollars. So let's read that, sorry. We cannot compare the two costs directly because inflation makes $1 today worth more. It buys more than $1 3 years from now, right? We need the two prices expressed in comparable terms. So we convert to so-called constant dollars, which just means dollars at the same time. We push things to the same time, then we can compare them. We take the car costing 22,000 3 years from now and ask, what would it cost in today's dollars? In other words, we convert the future value, which is 22,000, to its present value. Right? That's just what we said. Before we go, in the presence of inflation, the only way to compare prices at different times is to convert all the prices to constant dollars. We pick some fixed time. So it doesn't have to be now. We don't have to compare things now. So somebody else had the idea of comparing things after the 3 years. So they wanted to find what the future value of 20,000 would be. That's fine. You just choose any time and convert everything to that time, to its value at that time. So we pick some fixed time and compute future or present values as appropriate to determine what things would have cost at that time. There are some other interesting calculations related to compound interest besides present and future values. We will do one more of these examples. By the way, let me just say one thing. Sometimes in math we talk about theory and applications. Okay? Theory and applications. So what, sometimes I say, oh, do the students really know what I'm talking about? When I say theory versus applications, I don't know if they know. So, the theory is like the formula. And then the applications are all these particular problems that we've done. Like constant dollar problem, and inflation is another application, and compound interest is another application, and so on. They're all kind of applications of a theory. Okay, so we often talk in science and math about the theory and then the applications. The applications are where you apply the theory, the problems that you apply it to. Okay? So, we've done a bunch of different applications here. Okay, let's do one more. Effective interest rate. You have just won $1 million in the lottery and are deciding what to do with it during the next year before you move to the South Pacific. Bank 10 offers 10% interest, compounded annually, while Bank 9 offers 9.8% compounded monthly. Okay, so Bank 10 gives you 10%, and Bank 9 gives you 9.8%, okay? But the compounding periods are different. Bank 10 is what? Annually. Bank 9 is what? Monthly. Which is better, monthly or annually in general? Monthly. In which should you deposit your money? Okay, so before we just talked about we can't compare values at different times. We have to bring them all to the same time and then compare them. Like all to now or all to 3 years in the future. Now we have another problem, is we can't compare interest rates with different compounding periods. Okay? So we have to do something to figure it out. So let's calculate the future value of your $1 million after 1 year in each of the banks. Okay, so we just figure out what is it worth after 1 year if I put it in Bank 10 or if I put it in Bank 9. Okay, and that's an easy calculation to do. This one is 1.1 and Bank 9 is this one. Okay, everyone get that? Where does this calculation come from? This is the compound interest formula. What's the interest rate per period? It's 9.8% divided by 12. What's the number of periods? 12. So we get this calculation here, we get this calculation here. Okay, because it's only compounded once. Okay? Everyone agree? So we get two different numbers here, right? So which looks better? Bank 9, right? Okay, but they're going to do a little more, make another point as well. Bank 9 turns out to be better. It will pay you a total of $102,500 in interest over the year, whereas Bank 10 will only pay you $100,000. Okay? So you can make another point. Another way of looking at the calculation in example 5, this example, is that Bank 9 gave you a total of 10.25% interest. No, it didn't. What are they talking about? They said Bank 9 gave me a total of 10.25 interest. What is that about? Bank 9 didn't give me that. Bank 9 gave me what? 9.8. Why did they say 10.25? Huh? Total? What, this is a total of 9.8. What do you mean?
Like when it becomes like 102,500.
This number here, yeah.
The increase is like, it's increased by 10.
Ah, okay. So how much did it increase from the beginning of the year to the end of the year? 9.8%? No. It increased 10.25%, right? Okay? So we can say that's called the effective interest rate. Okay? So the interest rate was actually 9.8% compounded monthly, but the effective rate means what? What would it be if it was compounded annually? Just compounded annually. Okay? So if it was just compounded annually, what would it be? 10.25%. We call 10.25% the effective interest rate of the investment, also referred to as the annual percentage yield, or APY. How many people have heard of APY? Good, me neither. But I have heard of effective interest rate. Okay, but APY in the banking industry. And then, well, how do we refer to this, the 9.8%? That's referred to as what's called the nominal interest. Does anybody know the word nominal? Nominal? Was there any guess of where it comes from? It's a Latin word. Any guess of where, what it means in Latin? Or French, or Italian, or Spanish? Just the first three letters. Any Spanish speakers? French speakers? Italian? Or other Romance languages? You know what Romance languages are? Those are Latin-based languages called Romance languages because they come from Rome. Latin. So anybody speak any of those languages? Okay. N-O-M, it's like name. It's maybe the Spanish word for name, maybe a French word for name, something like that. Okay, name. So they call this the nominal interest rate. So we have the effective interest rate was what again? 10.25%. And we have 9.8 is the nominal interest rate, means in name only. Nominal means in name only. So it's not really this, but it's like just the name of it. Okay? So it's called the nominal interest rate. Okay? So do you understand? So what's the difference between the effective and the nominal? The nominal is like the stated rate, and the effective is what it would be if it was just simple interest over a year. Okay? In general, to best compare two different investments, it's wisest to compare their effective rather than nominal interest rates, right? So if we have the effective rate was 10.25, that's kind of better. It helps us better compare the two investments. Okay? And we saw that this was better than the 10% one, right? At Bank 10. Okay, they said, notice this. 1 plus this over 12 to the 12 equals this. And then subtracting 1 to get this, 10.25, right? Or, I'm sorry, 10.25%, right? So, we can write the formula. We take this thing with R nominal, 9.8, or 0.98, and divide by m to the m minus 1 gives you the effective interest rate. Okay? That clear? Okay, so this is the calculation for the effective interest rate. And he says in this video that you don't even notice that in this effective interest rate, you don't even need to know what the present value was, what the initial investment was. It's irrelevant, right? It's just the terms of the investment that give you the effective interest rate. This doesn't, in this calculation, we don't need to know PV, right? It doesn't matter what PV is, we still can figure out the effective interest rate. Okay? So, to compare rates of investment with different compounding periods, always compare the effective interest rates rather than the nominal rates. Okay? Alright, let's watch this video because you're probably sick of hearing me. So let's watch this video.
we have this $3,000, 9% monthly compounding 1 year. Let's just make. Suppose we have this $3,000, 9% monthly compounding 1 year. Let's just make the calculation. All right, here's our formula. The principal 3,000, interest rate 9%. N is 12 because we're compounding monthly, and then the time is 1 year. We find that the amount in the account is this amount. The difference between 3,000 and this number is the amount of interest. The interest then is $281.42. Now, I wonder how this corresponds to, or how it relates to the notion of simple interest. That is, the compounded quarterly.
It's very important for you guys to listen to this, or else you can't pass my class.
That's right. And look at this. Yeah. So we're lucky to have him. He just walked in at the right time. We were just talking about effective interest rate. What else were we talking about? Effective interest rate and constant dollars. What else? I forget already.
All those things, right?
Yeah. What else were we talking about? Anybody help? Effective interest rate.
Bonds.
Wait, a bond. Compound interest rate. What else? I don't remember. Let's check. Effective interest rate, nominal interest rate, APY. I'm just trying to impress it. Constant dollars.
Who's taken accounting already?
Zero coupon bonds, right? What are zero coupon bonds? Let's impress it.
One person?
What are zero coupon bonds? Impress
One
it.
guy. Zero coupon bonds.
No. Make me feel like I
Did something.
Yeah. What? Zero coupon bonds? Come on. No? Come on, please. What? I can't hear you.
We're too shy.
No, don't be shy. Help me. No?
What does it say?
Too shy. Anyway, they know.
What does it say?
Right? No. Okay.
Break it down. Break it
No,
down.
they know, right? You guys know, right? We're just not talking.
Okay, not talking.
No, they know it.
This is important stuff, guys, okay? Because if I don't spend a lot of time on it, and because we only have a certain amount of time to do everything we need to do, and you've already seen the size of the book you have to cover, right? The accounting book. So, this is the kind of thing that we have to go through pretty quickly. So anybody who's interested in finance, or who wants to be rich one day, or wants to investments, or who, I'm sure you all want to be rich. Who wants to be rich? Raise your hand. Okay, you have to understand this interest rate stuff. The richest people on earth, they make 3% and 3% and 3% and 3% and 3%. That's how they do it. Okay, so you got to understand this. So please listen up. Okay?
Okay, you heard it from the horse's mouth.
I'm just a pony.
Okay, so anyway, all right, well, I won't play the video since we got Professor Pardo instead. Okay, now we have annuities to talk about. So let's go to annuities. Okay. So are you tired yet? Okay, let's talk about what this word annuity is. Or actually, before we talk about it, let's look at an example. Okay, let's look at this example. Everybody ready? A sinking fund. What is a sinking fund? Okay, let's read it. Suppose you make a payment of $100 at the end of every month into an account earning 3.6% interest per year, compounded monthly. Okay, so you're going to put in how much again? $100 every month. In yen, what would it be approximately every month? About Ichima yen, right? So you're going to take Ichima yen and put it in Oita Bank every month, and you're going to earn 3.6%, which you don't really get at Oita Bank, but okay? Everyone get the deal? And this money is going to be compounded monthly. And we understand that now, so this is in a new section, but they're referring to compounding monthly, and they assume we already know what it means, and we do know what it means. Okay? This means that your investment is earning 3.6% divided by 12, which is 0.3% per month, right? I equals 0.003. What will the value of the investment be at the end of 2 years? Is this the same problem we did before? Not at all. Why not? Because the problem we did before, we just took one amount of money and put it in the bank. This is completely different, right? Shh. We're taking money, we're adding money in every month. So that's a completely different calculation, right? We can't go and use the same formula. Okay? And the question is, what will it be worth at the end of 2 years, 24 months? Anybody have a strategy for doing that? Well, the strategy is pretty straightforward. The future value is this. Now what is this? Where does this come from? Well, what is this 100 doing there? Any guess about that? What? The investment what? Can't hear. Okay, right, that's what I wanted you to say, but it's wrong. It's the investment in the first month. No, it's just the opposite of that. I mean, I didn't explain this formula to you, so you don't know what this is, but no. This is the investment in the last month. Let me explain. You don't get, notice one thing, they said you put $100 at the end of every month, okay? That was important here. Okay, you understand? Now why do I say this is the investment at the last month? Because I put in $100 when? At the last month, at the end of the month, right? Do I get any interest on that? Zip, right? I get no interest on it. So I'll just get the $100, right? That'll be part of the future value. Okay, so that was a hint. So what is this number? This is what? This is the second to last $100 that I put in. How long do I get interest on that? Just one period, right? Because I put it in at the end of the second to last period, it's in there just for the last period, right? Understand? Okay, then what's this term? This is the money, I put in $100 to the third to last period, right? That accumulates some interest, right? And it's a compound interest formula. And this is the formula, right? You get it? You get it? How about this one? This is the, sorry, what's this one? This is the first $100 I put in. Why is it only 23? Because when do I put the first $100 in? At the end of the first month. So it's only compounded for 23 periods, right? You get it? Okay, so this is the calculation. Or, it looks like we can factor out 100 here, and we get this calculation. Okay? Everyone see it? This is called a sinking fund calculation. What is a sinking fund? It's when you put the same amount of money in every period. That's called a sinking fund. This has a name. Sometimes you do that. That's pretty much like, similar to paying a mortgage. It's not, maybe not exactly the same, but it's pretty much the same as paying a mortgage. When you buy a house, you know, you might think, okay, you have, let's say you borrow $1 million to buy a house, and you have 30 years to pay it off. You haven't done this, you probably never even thought about it, so you don't know the terms that they give you. You might think that, like at the beginning, you have to pay more, and then at the end you pay less because you owe less, right? But that's not the way they set it up. The banks said, you could set it up like that, but they don't generally set it up like that. They set it up, you pay the same amount of money every month for the 30 years. That's the way that's the deal that they set up with you. That's kind of like this, right? We said you put in $100 every month, it's kind of like you're paying the same amount every month in your mortgage. So this similar kind of calculation will also work for a mortgage calculation. Okay? But anyway, so we can factor out the 100 here, and this is, again, called a sinking fund. And let's go on to see what it says. Now look at this picture, it's a nice picture. Here's the 24 months. What do we do here? We put in 100. What do we do here? We put in 100. What do we do all the way along? And every month we put in what? 100. Sinking fund means, I'm pretty sure it means you put in the same amount each time. Maybe I'm wrong. I think that's right. Anyway, so what does this line mean? This is to tell me I put in 100, this is early in the game, right? I'm putting 100 early in the game, I get a lot of interest here, right? Because it's in the bank for a long time. How much interest? I do 23 periods worth of interest, right? This one is the second month. It's in also for a long time. It's 22 periods of interest. And finally, this one, and this one, right? And then we're adding up all of this, right? Everyone get it? Fortunately, this sort of sum is well known to mathematicians. And there's a convenient formula for this value. Why do they say this? This doesn't look like anything. But it does. Look at it. What was the calculation? Let's go back. What was the calculation? If we kind of simplified it, this is the last line. It's 1 plus this squared plus this, It's something to a power. The same thing to a higher and higher power, right? Right? So that is exactly what this is. 1 plus x squared plus x squared plus Okay? This can be shown, and I'll do it next time, to be equal to this. Okay? So then, the future value will be equal to what? What was the number that was x? It was 1 plus 0.0 of this thing, minus 1, and then x again, 1 plus this thing, minus 1, and this one has to be the 24th. And we can easily do this in a calculator. And what's the answer? What's the answer? 248465. Okay? Everyone get the idea of this? Okay? The future value of a sinking fund. A sinking fund is an account. Okay, I was wrong. It's not the same, doesn't have to be the same amount every time. Okay? But a sinking fund is an account earning compound interest into which you make, what's that say? What's this say? From here to here. Into which you make what? Periodic deposits. Periodic means the periods are fixed. So every month or every 6 months, but it has to be the same time every month. Suppose that the account has an annual rate of R compounded M times per year, so that I equals R over M is the interest rate per compounded period. If you make a payment of PMT at the end of each period, so what's the PMT stand for in the last example? What was PMT in the last example? That's the amount that we paid at the end of each period was what? $100, right? Is everybody paying attention? Then the future value after t years, or n equals m times t periods, will be this. Okay? And we can show that. All right, so that is our introduction to annuities. Annuities, loans, and bonds. Okay, let's just read this first paragraph and then I'll let you go. A typical defined contribution pension fund, whatever that is, it's like when your company pays part of your pension, works as follows. Every month, while you work, you and your employer, so this happens in Japan, it happens in the United States, I don't know what other countries it happens in. You and your employer deposit a certain amount of money in an account. This money earns compound interest from the time it is deposited. When you retire, the account continues to earn interest, but you may then start withdrawing money at a rate calculated to reduce the account to zero after some number of years. This account is an example of an annuity. An account earning interest into which you make periodic deposits or from which you make periodic withdrawals. In common usage, the term annuity is used for an account from which you make withdrawals, but it could also be payments. There are various terms used for accounts into which you make payments based on their purpose. Examples include savings accounts, pension fund, and sinking fund. So these are basically all where you make payments into it. A sinking fund is generally used by businesses or governments to accumulate money to pay off an anticipated debt. But we'll use the term to refer to any account into which you make periodic payments. Okay? So that's fun, right? Okay, that's all for today. Thank you for your patience. See you next week.